Hi everyone, we start with Unit 2, Computational Thinking and Programming, and we are going to start Chapter 6, that is Introduction to Problem Solving. The topics covered are analyzing a problem, using decomposition, pattern recognition, making a model, designing an algorithm, algorithm corner cases, creating flowcharts, and pseudocodes. We start with problem solving. Computers can be used to help us solve problems. However, before a problem can be tackled, the problem and the ways in which it could be solved needs to be understood. So computational thinking allows us to do it. Computational thinking also allows us to take a complex problem, understand what the problem is, and develop possible solutions. We can then present these solutions in a way that a computer, a human, or both can understand. Now, computational thinking consists of 4 parts, that is decomposition, pattern recognition, abstraction, and algorithms. We start with decomposition. We need to start by looking at a problem and understand how it can be resolved. And one of the best ways to do that is by decomposition, that is breaking down complex problems into smaller, more manageable, and easier to understand parts. Now, these smaller parts can be examined and solved or designed individually as they're simpler to work with. So why is decomposition important? If a problem is not decomposed, it becomes much harder to solve. Dealing with many different stages all at once is much more difficult than breaking a problem down into a number of smaller problems and solving each one at a time. Breaking the problem down into smaller parts means that each smaller part or smaller problem can be examined in more detail. Let's start by looking at an example where you and your friends decide on creating an app. Now, the following questions could be a great place to start. What kind of an app do you want to create? What will the app look like? Who is the target audience? What will the graphics look like? Would you like to include audio? What kind of audio will you include? What software will you use to build your app? And how will the user navigate your app? How will you test your app? And how and where will you sell your app? Now that we've broken down the problem into much smaller parts, each part could be taken up by an individual, one of your friends, and whoever has the competency for whichever task can take up these, and it becomes a much simpler problem to solve. Let's look at pattern recognition. After we decompose a complex problem into small manageable parts, it helps to examine smaller parts for similarities or patterns. These patterns can help us to solve complex problems more efficiently. So what are patterns? Suppose you're creating a short animation movie that involves a lot of horses. We start off by considering the common characteristics of a horse: mane, body, legs, mane, tail. In computational thinking, these characteristics are known as patterns. Once we know how to describe one horse, we can describe others simply by following different specifics. So one horse may be brown in color with short tail and no mane. The other horse may be black and white in color with a long, thick tail and thick mane. So we have a basic pattern. We keep making all the changes on that basic pattern. We come to creating a model. Now, a model is a general idea of the problem we are trying to solve. So, for example, a model horse would be any horse, no specific horse, no specific color, a long tail or a long mane. We have a model that represents all horses, and from our model of the horses, we can learn what any horse looks like using patterns all horses share. Once we have the model of our problem, we can design an algorithm to solve it. That brings us to algorithms. Now, if we want to tell a computer to do something, we have to write a computer program that will tell the computer step by step exactly what to do. Now, this will need planning, and to do this, we use an algorithm. Algorithms are often the starting point for creating a computer program, and they're written along with a flowchart or a pseudocode. An algorithm is the steps or instructions written in plain English language and can be as simple as and as complex as required, depending on the problem at hand. Algorithms must always have finite number of steps, and each instruction is identified and the order in which these should be carried out is planned. Now, the advantage of having an algorithm is that you can save the time and the effort and write programs much quicker in any programming language based on those algorithms. It is important to plan out the solution to a problem to make sure that it will be correct. Using computational thinking and decomposition, we can break down the problem into smaller parts, and then we can plan out how they fit back together in a suitable order to solve the problem. So let's look at an algorithm to add three numbers. We start with step 1, start. Step 2, declare variables num1, num2, num3, and sum. Step 3 is read the values num1, num2, and num3. Add is step 4, and assign the result to sum. And step 5 is display sum. Step 6 is stop. Let's start with an algorithm to check whether a number is positive or negative. Step 1, start. Step 2, declare a variable num. Step 3, read the value of num. And step 4, if num is greater than 0, display it's a positive number. Else if num equal to 0, display the num is 0. Else display the num is negative number, and stop. Now let's look at corner or edge cases in algorithms. We start with an example where we are taking an input of 3 numeric values for each side of a triangle. And if the 3 sides are equal, it should give an output. It is an equilateral triangle. If any 2 of those sides are equal, it gives an output. It is an isosceles triangle. Otherwise, it says it's a scalene triangle. Now, in case the user inputs 3 zeros, in that case, this should not give us an equilateral triangle, which it will. In case the user inputs any negative value, it should not give us any output because length cannot be negative. And if the user inputs such values that the sum of any 2 is not greater than the third side, then we are actually breaking the rule of the triangle sum property. That is, 2 sides should always add up to the greater than the third side. Now, in case we need to handle corner cases, we have to mention or give a statement which makes sure that these kind of problems do not occur in our algorithm. So here we've shown it in red color. That is, if any of the sides is less than or equal to 0, and if the sum of any 2 sides is less than or equal to the third side, then it will give us an output saying not a valid input. So we have handled the corner cases in this example. We now come to flowcharts. Flowcharts visually present the process of solving problems and are drawn according to steps described in an algorithm. So it's a diagram which actually represents instructions, and each instruction has a standard symbol. So the advantage of flowcharts is that it's a great analytical tool during the development stage and acts as a blueprint for complex programs. When creating large computer software, a flowchart can provide a clear picture of the logic and flow of control, which is easy even for a non-technical person to understand. It is also very effective in finding errors which can prove very expensive later in the programming stage. Some of the symbols used in a flowchart are oval for start and stop. There's parallelogram for input and output statements. For processing statements, there's a rectangle. And for decision-making statements, we use a rhombus. We use arrows for flow of control, and for connectors, we use circles. We now look at some programming constructs, which are basically the kind of flow the program has, and these are helpful even in algorithms, flowcharts, and pseudocodes. So there's sequential construct, there's a selective construct, and there's iterative construct. The sequential construct means the program is simple. Each line will run one after the other. It will run from top to bottom. Selective means that in this construct, if the condition is met, the next few lines are executed. Otherwise, the computer ignores these lines and goes to some other part of the program. In iteration or iterative construct, we want the computer to execute the same lines of code over and over again. Now, all these three codes are sometimes used in combination with each other. Let us now look at the sequential construct, where we see an example of simple interest. We simply take the input, we calculate the interest, and we print that. So this is one instruction after the other and in a sequence, so hence a sequential construct. Let us look at an example of selective construct, where we take an input from the user and we check the remainder after dividing the number by 2. If the remainder is 0, the number is even. If it is not, it is odd. So we use selection here. So if it is true, n is even. If it is false, n is odd. Let us look at an iterative construct flowchart, where we have two variables, sum and n, and we've taken them as 0 to begin with. We keep incrementing n and adding it to sum till the time n becomes equal to 50. So the steps of incrementing and adding to sum keep repeating till such time that n is actually equal to 50. Then it prints the sum and we end it. We come to pseudocodes. Now, while algorithms are written in plain English, pseudocodes are written in a format which is similar to the structure of a programming language. It is an informal description, so it does not require the strict programming language syntax or technical considerations. It is used for creating an outline or a rough draft of a program. Now, it is not an actual programming language, so it cannot be compiled or interpreted as an exe file. We have some simple keywords and verbs for programs before it is actually converted into a specific programming language. So these keywords can be do, while, end, do, until, end, do, case, end case, if, end if, and call or return. And the verbs could be generate, compute, process, reset, set, increment, calculate, and operators such as plus, minus, multiplication, division. Even words like add, sum, subtract are used. Let's look at a pseudocode to find the average of 10 scores. We set total to 0, counter to 1. While counter is less than or equal to 10, input score, add score into the total, set the score average to the total divided by 10, and print the score average. If you notice, we have also done some indentation after while. That is basically to say these two lines after while are a part of that while statement. Okay, we look at a pseudocode for bubble sort, where we will repeatedly go through some steps to sort a list by comparing two adjacent items and swapping them if they are in the wrong order. So this is basically to either sort ascending or descending depending on the program. Now we start with set n to a number of records to be sorted. Repeat the following steps, that is set a flag to false. Then for each pair of keys, that is the two adjacent items, if the keys are in wrong order, then swap the keys and set the flag to true, end if, and go to the next pair. And until the flag is not set, we keep repeating this. That means that if the flag remains false, so all the numbers are compared and they are sorted, so we no longer need to swap. So pseudocodes can be written in multiple ways, just like algorithms and flowcharts. So here is a way of doing it more technically, which becomes even easier to change into a program. We set n to number of records to be sorted. Repeat, set flag is equal to false. For counter is equal to 1 to n minus 1. We say do if key counter is greater than key counter plus 1, then swap the records. Set flag is equal to true. End if, end do, n is equal to n minus 1 until flag is equal to false or n is equal to 1. So there are multiple ways in which you could write your pseudocodes, your algorithms. We have to check out which is the best way. So that brings us to the end of chapter 6. This is just the beginning of programming, and we will be going from here to Python very soon. I hope to see you in the rest of the lectures. Bye-bye.